Hi everyone, I'm Radoslav, and today I'm going to be talking about another problem from the recent CodeChef Long Challenge, which was the first contest for 2021. So let's get to the problem. So the problem was called Curious Matrix, or CURMAT, and it was mostly about some math concepts, but then you had to actually reduce it to a graph theory problem, which is actually the cool part in the solution. But without further ado, let's go to the problem statement. All right, so basically in this problem, first we are given a bunch of definitions which are like from maths. And the first one is basically a matrix, but I guess everyone is familiar with them. Like we have a square n by n matrix. And then we also have the definition of determinant, which I'm not gonna explain in this video because, as I have mentioned in the past, I'm trying to keep this videos shorter. And yeah, like if you don't know the definitions for determinant or submatrix, although submatrix is very simple, I advise you to check them before going to the video. And yeah, basically we are gonna say that a matrix is curious if all of its submatrices of size at least 2 have their determinant being a multiple of P. Or in other words, we basically just have the constraint for every curious matrix. Like for every curious matrix, we want the determinant of all of its submatrices to be equal to 0 modulo P, which is like equivalent to the determinant being a multiple of P. And I mean, this is our constraint for a matrix being curious. In other words, we just want all of its submatrices to have determinants equal to 0 when we consider them modulo P. And yeah, basically like this is the definition of a curious matrix, which is given in this problem. And our problem is actually slightly harder because we actually have queries which are up to 10 to the 5. And we can also notice that our matrix is relatively large. It's up to 10 to the 5. And what we have is basically every query means that some value will get a new value, some cell will get a new value. Or in some sense, we have a matrix where some of the numbers are filled and others are still not decided. And we are interested in finding the number of ways we can actually fill the rest of the values so that the matrix becomes curious. Yeah, to just recap everything, we basically have queries. Initially, our matrix is empty and we haven't filled anything. And every query is either we set some cell to a value or we just empty a cell so that it won't have any value in it. And after every query, we are interested in finding the total number of curious matrices that can be that we can get by filling the empty values. And yeah, like here we can see the sample, and we have 4 subtasks. Like the last one is for the final solution, and the rest of the subtasks are as follows. The first one, we basically have a small n and the small q. Then the second subtask, basically, it says that no two queries will actually affect the same cell, which means that basically we will never empty a cell. Or in other words, initially we have an empty matrix and we just repetitively add a new cell to it. Like we just fill the table. And after every query, we are interested in finding the number of ways to fill it up. And then there is another subtask, which may seem kind of weird, but you'll see later on why it's there, and I'm gonna explain. We basically have this subtask where there is always at least one way to construct a curious matrix. Because also in the solution it says that if there is no, we are basically given a partially filled matrix, and we are interested in the number of ways to complete the other cells to make it curious. But like sometimes it may happen that from our partial filling, we can't really get any curious matrix. And then we need to output 0 because like there are no ways to actually get a curious matrix from the current filling. So yeah, in those cases, I mean, there is like this subtasks, which is like the third one, in which we always have at least one way. And this actually helps us quite a bit while implementing it. And that's the main reason we actually have this subtask. All right, so I guess let's go to the solution. And I'm going to mention it here. If you already, if you already have some observations and you just want to look at some hints or something like that, I'm going to explain just like the steps in the end of the video. So there should be a link here or in the description of the video to the last couple of minutes, which would be like 2 or 3 if you just want to see a couple of hints and you don't really want to go through the whole solution. So yeah, if you don't really want to watch the whole video, go to the description and look at the hints, which will be in the end of this video. But yeah, let's actually start with some intuition. And you can already see here a spoiler, which is that we are going to consider 2x2 matrices, 2x2 submatrices for this problem. So yeah, let's get right into it. All right, so basically what we want for our matrix is to have all of the determinants of its submatrices being equal to 0 when considered modulo P. That's literally our problem statement. And a good thing to begin with, because determinants are pretty hard to compute in general. You have to use Gauss or something like that if you have just like a large matrix. So let's try thinking about something that's easy to compute. And like the determinant of a 2x2 matrix is very easy to compute. It's just the difference between the diagonals. Like it's the difference between the main diagonal and the secondary diagonal. And yeah, we basically want this to be equal to 0. And this is like a necessary condition because, yeah, we want the determinants of all submatrices to be equal to 0. So this means that we also definitely want all 2x2 submatrices to have their determinants equal to 0. And surprisingly, it turns out that this necessary condition is also a sufficient condition. Or in other words, if we have a matrix such that the determinants of all 2x2 matrices are equal to 0, then the determinant of all submatrices will be equal to 0, which is a pretty cool thing. I'm going to not formally prove it, but I'm going to give the intuition why it's correct. So yeah, let's get straight to that because that's one of the interesting part of the problem, because yeah, you'll see. All right, so let's just consider a small 2x2 matrix, which has like, yeah, you can just see the values here. And as I said, the determinant is the difference between the product of the values on the main diagonal minus the product of the values on the secondary diagonal. So it's just like, yeah, you can see it here. And what we want is this thing to be equal to 0 modulo P for all submatrices. Yeah, like this here is just some random submatrix. Or in other words, we can actually rewrite here, rewrite this by substituting the determinant from the above equation. And we are going to get that we want the product of the first diagonal to be equal to the product of the second diagonal, modulo P. But from now on, I'm just going to ignore the modulo everywhere, because in the problem, we can notice that all values are between 1 and P minus 1. So like the 0 is excluded. So like if you see somewhere an equality, the equality is under the modulo P. So yeah, we are just going to consider everything modulo P. And okay, like this gives us basically a constraint, which is that if we have four adjacent cells, like a 2x2 submatrix, then we want the product of the main diagonal to be equal to the product of the secondary diagonal. And let's imagine that we have fixed 3 of the cells, let's say those 3, and then we have a cell that we still don't know anything about. like this x, we can actually notice that x will be equal to basically this product over, yeah, great, I actually have a typo here. It should be over a1, because like it's, yeah, sorry about that. It's basically just, I mean, it's basically like the above equation, but I just substituted a22, like this cell, by x, and we can get like this value. The division here, by division I mean we just get this, the value we divided by, and we just find the modular inverse. So it's like to the power of p minus 2. But like, it's easier to explain if I just have it as division here. As again, I said that everything is modulo p, and we have all operations modulo p because the values are from 1 to p minus 1. But yeah, I mean, like, if we have those three cells and this cell x, then we can actually find the value x by those three cells. Because, I mean, we have this constraint. So if we know those three values, we can determine uniquely x, because it's just equal to this thing. All right, so let's actually consider a larger case. Oops. So we have x here, and yeah, we already know that x is equal to the product of those two. So it's the product of a21 multiplied by a12 over a11. So let's just write it here. So it's this thing. However, now we can notice this rectangle, which is like basically the one I'm hovering above. And you can notice that we can apply the same rule. So we know that the cell on the second row, like the rightmost cell on the second row, will be equal to the product of those two cells over this cell, by using the same rule, but for this submatrix. And then the things will cancel out, and we are going to get that this cell will be fixed, and it will be equal to a21 multiplied by a13 over a11. And by repetitively doing this, we can notice a pattern, that if we have fixed the first row and the first column, like the leftmost column and the topmost row, then all other values can be uniquely determined. And actually the value will be equal to, so I mean, for some cell, its value will be equal to the value of the leftmost column, which is here a21, multiplied by the value of the topmost row at the current position over a11. So it's like the first cell. This is if we have fixed the first column and the first row. I advise you here to actually stop the video, and if you want to gain some more intuition, to just fix the topmost row, the leftmost column, and to try deduce all of the values. And you are going to notice the pattern that every value is equal to the product of the value on its row multiplied by the value on its column divided by the first value, or like the a11 value, because we have also fixed this one. And this is only by using the 2x2 determinant rule. So yeah, actually this is the main thing we are going to use in our solution to, I mean, not in the solution, but in the idea. So I mean, like, we already have some form of every cell if we have fixed every, well, like if we have fixed the topmost row and the leftmost column, we already have a form for every cell. So let's just consider 4 random cells, like not random, but let's consider 2 rows and 2 columns, and consider the 4 cells that are formed by them. So it's like we basically just pick 2 cells, which are x1 and y1, and x2 and y2. So it's like those 2 cells. And let's consider the rectangle that's formed by those 4 cells. And now let's consider the submatrix that's, it's not really a submatrix, but like let's form the matrix that's that basically just consists of those 4 cells in this order. So it's like this cell is above this cell, and this cell is to the left of this cell. And yeah, I mean, like, it's just if we just like erase the empty spaces, let's just consider this determinant. And you can notice that if we find the determinant of this table, which is formed by those 4 cells, it turns out that it's also equal to 0 by using the forms we described before. You can write down the math, and it's pretty fun, because like this means that if the determinants of all submatrices are, all 2 by 2 submatrices are 0, then we also have the fact that the determinant of any 4 cells, like any 4 cells like that, is also 0. I mean, by the matrix that's created by those 4 cells. And this is actually the fact we are going to use to prove that the determinants of all submatrices for sizes greater than or equal to 3 are also 0. And this is because we can use the Laplace expansion, which is which you can check here, but it's like a theorem for computing the determinant. It basically states that we can pick some row or some column, and then we can express the determinant of a matrix as a sum of the determinants of smaller submatrices. In other words, like, I mean, if you are not familiar with it, I advise you to check it, but basically when we use this thing, we are gonna end up at the form of our matrix as a sum of the determinants of 2 by 2 submatrices, which may be of just any 2 cells. I mean, like, in the end, we are gonna end with a form that's like, in the end, we can express the determinant of the whole submatrix as the sum of the determinants of such submatrices, like from 4 cells like that. And this is pretty cool, mostly because we already proved that the determinant of all such submatrices is equal to 0. Therefore, the whole determinant will also be, the determinant of the whole submatrix will also be equal to 0 when we consider it modulo P. This may be a bit weird, so yeah, you can, if you're unfamiliar with what Laplace expansion is, I advise you check it out. It's a pretty simple formula, but yeah, using it, we can basically just prove that the 2 by 2 determinant condition is not only necessary, but also sufficient. And this simplifies the problem quite a bit. However, we also need to use this fact we showed, that if we fix the first row and the first column, then all other cells can be uniquely determined. And that's this, and the 2 by 2 observation are basically the main parts to solve this problem. And yeah, now let's go to the solution. So yeah, this is again as a recap. Now we showed that if we have all 2 by 2 submatrices determinants equal to 0, then the determinant of all submatrices will be equal to 0. And yeah, we basically just showed that. And now imagine that we actually have some cell, and we have already fixed its value to be v. Like, imagine that we just have a query which is a cell xy will have a value equal to v. Now we are going to the solution, and we are going to start it by considering just a cell, and let's fix its value to v. However, we also know that this cell has a value equal to the value of basically like the first value in its row multiplied by the first value in its column divided by A11. That's from the observation we showed using the 2 by 2 submatrices determinants. So, you can already figure out, if we just substitute AXY by V here, we are going to get a constraint, which is basically V multiplied by A11 is equal to the first value in the row multiplied by the first value in the column. So in other words, we have constraints of this form, like V multiplied by the 1 value is equal to the first value in some row multiplied by the first value in a column. And surprisingly, if you actually also consider, this is correct if x and y are greater than 1. or basically when the cell isn't from the first row or the first column, because we showed it for all other cells. However, we can notice that this is also correct if x or y are equal to 1, mostly because just the a11 will cancel out here. So yeah, even if we have a query which is ax1 is equal to some value, the above will be correct, which is just nice to notice, because it gives us, I mean, it's basically a simple way to fix a value of the first row or column. I'm not sure whether I explained it very well here, but what I wanted to say is just that the below constraint also works if x and y are equal to 1, because the a11 will cancel out, which is pretty useful for the later part of the solution. And yeah, like in some sense, we just have constraints between the values in the first row and the first column. Actually, it's the other way around. It's the first row and the first column. But yeah, we have like constraints which are of the above type. And now what we can do is that we are going to create a graph. And I'm going to call this a constraint graph, where every variable will basically correspond to one of the cells from the first row or the first column. Or in other words, we have 2n minus 1 vertices, where every vertex corresponds to some cell, which is on the first row or the first column. It's 2n minus 1 because we don't really want to have two variables for the a11 cell. I mean, we just have a11 once. So yeah, we have those vertices, and an intuitive thing to do is to basically just have the constraints as edges, because I mean, we have a graph, we have decided to have all of the cells that we don't know anything about as the vertices, and I mean, then the constraints in some sense can correspond to edges. And yeah, I mean, if we have, as we have 2n minus 1 vertices, let's just say that if we have a constraint of the above type, let's just say that we have an edge between x1, like this vertex, which is defined for basically the cell, and the other cell which is for y. I mean, the second one is basically from the row cells with weight equal to this v, which is basically the value of the cell. Okay, so now we basically just have constraints and vertices, and what we want is in a way to fix the value of every vertex such that the product, I mean, basically our constraints are that the product of two cells over the value of the first cell, which is a11, should be equal to v. Or in other words, v multiplied by a11 should be equal to the product of some two cells when we have an edge. But let's actually first think what will happen if, I mean, imagine that we have such a graph with some vertices and some edges. What will actually be the answer? Well, it turns out that the number of possible matrices is equal to p minus 1 to the power of number of connected components. Here it's p minus 1 because we have the explicit constraint that the values that we can fix for all vertices are from 1 to p minus 1. So it's like overall it's p minus 1 values. In other words, what this means is that if we fix something from a connected component, then everything in this connected component can be uniquely determined. And I mean, like, you can easily convince yourself that this is correct. Mostly because if we have fixed some value, then we can just work out using v and the other part of this equation to uniquely determine the other value. So yeah, basically what we have is that if we, I mean, yeah, that's pretty much it. I mean, it's not that hard to basically get this thing. mostly because we can actually start from the empty grid and to actually, like consider the empty grid, which is with no cells. And you can actually try finding it by hand, like the number of possible solutions, and you're gonna end up with p minus 1 to the power of 2n minus 1. So this basically leads you to the fact that everything can be determined by the first row and the first column. And yeah, after that, you can just fix a couple of cells and see how the value will change, either by running a brute force or some other solution. And yeah, after you figure this out, you can notice that the answer is always p minus 1 to the power of the number of connected components. However, this is correct only if there is at least one solution, because it may turn out that some of the constraints will actually break the whole curiosity of this table, and the answer will be 0. And in such situations, you can't really easily tell. I mean, like, it's hard to tell when some of the new constraints break the previous constraints. So that's why we actually have the subtask 3, which I mentioned. I'm going to go back to the problem statement for a second. So remember that there was this subtask where after each query, there is at least one way to construct a curious matrix. So in other words, the answer for every query will always be p minus 1 to the number of connected components. And I mean, in this case, you can simply notice that we just have the problem, which is we are given a graph, and all constraints are just add an edge between two vertices. And now after every query, you're interested in finding the number of connected components. And then you just use fast powering, or you just pre-compute the powers of p minus 1. So yeah, that's a relatively simple solution for this subtask. But you can actually, I mean, like, it's not very hard to actually extend it to the full solution, because now the only thing we need to add is to basically find when some constraint breaks the previous constraints. And for this, you can actually think about what will happen when you add basically, what will happen when we add an edge. When we add an edge, there are two cases. The first case is basically we are gonna just unite two components that weren't connected. And in this case, we already figured out that one value can actually determine everything in both connected components. And yeah, I mean, like, if that's the case, then you can just simply unite the two components. And in the other case, we actually create a cycle. And when we create a cycle, we basically have the problem that we want basically the value of, I'm just gonna go to the slides, but you can already see from the slides, I mentioned here that we are gonna create a disjoint set union, where we are gonna represent the value of every vertex as a function of its component root. Or in other words, we have basically like a value of some vertex v is equal to, we have this function f of v, which we are going to apply to the value of the root. This basically just means that the value of every root will be expressed as this function fv of the value of the root. And I mean, like, we're going to try maintaining this value function for every vertex. And yeah, I mean, like, what we need to notice, which is maybe the hard part, is basically that the form of this function is actually relatively simple. It's basically, not relatively, it's not very hard. It's basically a coefficient multiplied by the value of the cell, the main cell, or like the cell which is from 1, 1. Like basically the origin, to some power of p multiplied by x to the power of q. X is basically the function we apply the result to, where p and q, which are the powers, are either -1, 0, or 1. So this is mostly because all of our edges actually cross the graph. We basically have all of our edges are between a vertex between a row vertex and a column vertex. And in some sense, like, we can never have a path of two consecutive row vertices, or like a path between two column vertices. Or in other words, our graph is, I mean, not really bipartite, but like, yeah, in some sense it is. So yeah, basically what I want to say is that, yeah, it's actually bipartite. Like we always have an edge between a row vertex and a column vertex. And using this, we can actually show that we can always express the value of some cell as a function of the value of the root, and it will follow the following rules. Everything I say right now can be actually derived from only by the constraint rule. And I'm gonna actually, I don't really want to write it here in the video editorial because it doesn't really make sense, because it's just like some mathy stuff which you need to figure out by hand, and it will be just, I mean, if I tried showing it in the video, it would have literally been just me writing some formulas. And yeah, I decided to just leave the final form, which is basically just the main cell to a power multiplied by the result we applied this function to, multiplied by some coefficient. And like, we just take everything modulo p. So yeah, I mean, at this point, we can basically see that the problem happens when we actually have a cycle. I mean, like, because as I said before, if we just unite two components that don't really have a cycle, then we can just express one of the roots by using the other root. It's not that hard. You just take the inverse of this previous function, which is, as we have like very simple, I mean, the form is very simple. It's just a product, and the powers are also very simple. Then taking the inverse is very easy. And if we have two components that don't, I mean, like if an edge doesn't create a cycle, we are just gonna express one of the roots as a function of the other root. And yeah, I mean, that's literally it. And in the other case, if we actually create a cycle, we want to ensure that the value of some vertex u multiplied by the value of some vertex v is equal to w multiplied by this main cell, which is a11, modulo p. And I mean, if this isn't satisfied, then the answer for all other queries is basically 0. And yeah, we are done. And yeah, how we can do this? We basically just calculate the value of u, we calculate the value of v using the root. I mean, the root is the same because we have a cycle. So we basically know those two values, and we know w, and we just need to check whether this is satisfied. And what we can do is basically just express everything using the root, and then check whether it's equal to w multiplied by a11. I mean, we get this expression as like a function from before. Then we get the other expression, we multiply them. It's easy to multiply them because like the form is just a product of some terms. And then we just like divide by ai and check whether it's equal to the w value, which we know. So yeah, I mean, like, if this is satisfied, we can just continue. If it's not, we can just, yeah, I mean, like, we just know that the answer for all queries until we erase this edge is 0. So yeah, I mean, like, at this point, I guess it's the best thing to do is to just like go to the final solution. I mean, like, before that, just as a note, the second solution, like the second subtask, is basically just implement disjoint set union with this value x representation, because in the second subtask we never actually remove cells, and if at some point this isn't satisfied, the answer for all subsequent queries is 0. And yeah, like, for the final subtask, we basically just need to use the previous trick, but we also apply the offline dynamic connectivity idea. And I have left a block here. It's, I mean, it's a pretty nice way to convert some problems with additions and removals to just an offline version with just additions. But the only constraint is that our data structure, which we use, should be able to revert its changes. By revert, I mean that it would be persistent, or we can do rollbacks on it. But fortunately, the disjoint set union is such a structure. And I mean, this is just one of many tutorials or blogs which actually share this idea. And if you want to go into more details, I advise you to check the editorial of this problem, because there'll most likely be another link to some other blog about the offline dynamic connectivity idea. And yeah, I mean, the complexity will be n log squared n. So yeah, that's pretty much the solution. It's on a higher level because that's a problem where you actually need to work out the details by your own on like a piece of paper to get the actual intuition why everything works, because it's like slightly more mathy. I tried giving the main ideas, but I actually haven't shared a lot about how to implement the idea with the functions. So it's on a higher level. I apologize for that, but hopefully it was good enough. And now, as a final note, I'm gonna again give like just a recap of the whole solution. So, I mean, we have this problem, and a lot of people will probably think that there will be a lot of math involved, or you'll have to read some paper or something like that. However, for this problem, the best idea was to actually start it by considering some simple case, or like in this case, it's just like some determinants that are easy to calculate. And I mean, the first thing that should come to our mind is like 2x2 matrices and maybe 3x3 matrices. But like we should always start with the simpler thing, so it's like the 2x2 matrices. And yeah, like basically when we have the 2x2 matrices, it's not that hard to actually notice that only the first row and the first column matter for the whole configuration. And if you notice that, you already have the closed form for every cell. And from the closed form for every cell, it's not that hard to notice that we can create a graph where we have basically just 2n minus 1 vertices, and the edges now will represent the constraints. So yeah, now what should come to our mind is okay, we have this graph, but how to find the number of solutions? And it turns out that it depends on the number of connected components. The best way, or like in my opinion, the easiest way to notice this is to first consider some extreme cases. In our problem, the first extreme case that should come to our mind is when we have no edges. And yeah, we notice that it's just 2 to the n minus 1, like p minus 1 to this power, like p minus 1 to the power of 2n minus 1. And yeah, in this case, like we can obviously see that this is equal to the number of vertices in our graph. So yeah, you don't have any edges, and the answer is p minus 1 to the power of the number of vertices. And then when you add just one edge, you can see that basically the answer just becomes to the power of 2n. So in some sense, the answer just depends on the number of connected components. And well, if you have figured this out, it's quite easy to notice that everything just depends on the number of connected components. And yeah, like you should immediately get a solution for the third subtask, which was when we don't really have, when we always have at least one solution, because it's literally just computing the number of connected components with additions and removals of edges, which is a standard problem. And after that, you need to work out how to find the cases in which we don't really have a solution. And yeah, you can notice that this happens when we have a cycle. And from there, you can actually get the idea of keeping a representation of every vertex as a function of the root of the component. And using this, it's actually relatively easy to check whether the cycles will break the curiosity of our matrix, or like the partial matrix. And yeah, the final part is basically just apply the offline dynamic connectivity to this solution. And yeah, that's pretty much it. If you have some questions, leave them in the comments or of this video or on the editorial on the CodeChef page. And yeah, thanks for watching.